Aerial footage of iconic sea bridges. Bridges, they connect cities, unite communities, and keep the world moving. But have you ever wondered how engineers build these massive structures over deep, unpredictable water? Hello, welcome back to Civil Engineering Edge. Ever wondered how massive bridges stand tall over deep oceans? Let's dive into the engineering secrets behind these modern marvels right now. In today's video, we're diving deep, quite literally, into the fascinating world of how bridges are built over deep water. From underwater site analysis to concrete piers rising above the surface, we'll explore the step-by-step process, using real-life engineering marvels like the Confederation Bridge in Canada as our guide. 1. Site analysis, the first step beneath the surface. Before a single piece of steel is placed, engineers must conduct a comprehensive site analysis. This involves studying water depth, current strength, seabed or riverbed soil conditions, tidal movements, and weather patterns. For example, when building the Confederation Bridge, which stretches 12.9 kilometers, 8 miles across the Northumberland Strait, engineers had to assess water depths ranging from 45 meters, 148 feet, to 60 meters, 197 feet. They also had to consider strong tidal currents, harsh winter ice, seismic stability, accessibility for construction machinery. The goal: to choose a location that not only minimizes construction challenges, but also ensures long-term durability and cost-effectiveness. 2. Bridge design. Engineering meets imagination. Once the location is finalized, the next step is designing the bridge. This involves answering key questions. What type of bridge is best suited? Suspension, cable stay, or beam bridge? What will be the size, shape, and structure of key components like piers and deck spans? How much load, stress, and environmental force must it withstand? Using advanced computer modeling and simulations, engineers ensure the bridge design can withstand everything from heavy vehicle traffic and high winds to the unpredictable force of deep water. 3. Choosing the right bridge type. Strength meets strategy. Not all bridges are built the same. In fact, the type of bridge selected plays a major role in its success, especially over deep water. Let's take a quick look at the most common bridge types. Beam bridges. Simple and cost-effective, ideal for short spans over narrow water channels. Arch bridges. Perfect for valleys or locations with solid foundations. Their curved shape naturally distributes weight. Suspension bridges. Designed for very long spans, often exceeding kilometers. Think Golden Gate Bridge or Akashi Kaikyō Bridge. Cable-stayed bridges, a modern favorite for medium to long spans, combining beauty and efficiency with fewer anchor points. Visual diagrams of each bridge type with real-world examples. The choice depends on many factors: the span length, the terrain and water depth, expected traffic and weight loads, budget and material availability. For instance, when building Japan's Akashi Kaikyō Bridge, engineers opted for a suspension bridge designed to span an enormous 1,991 meters, 6,532 feet, the longest of its kind at the time. 4. Sizing the structure. Every detail counts. Once the bridge type is finalized, it's time to design the individual components, down to the last bolt. Engineers calculate the size of beams and girders, strength of cables and anchorages, shape and spacing of piers and towers. Why so precise? Because these structures must handle the weight of the bridge itself, the vehicles, trains, or pedestrians crossing it, environmental forces like wind, waves, and earthquakes. Advanced modeling tools simulate these forces to ensure stability and durability before construction begins. 5. Preparing the site, laying the groundwork below water. With the design locked in, the next step is site preparation. And in deep water, this phase is both crucial and complex. Site prep may involve dredging the seabed to reach solid layers, building temporary platforms for workers and equipment, installing cofferdams or caissons to keep water out. Building underwater foundations is one of the most complex and critical stages in constructing a bridge over deep water. To support these massive structures, engineers rely on specialized techniques like caissons and cofferdams. Caissons are watertight structures, often made of steel or reinforced concrete, that are sunk into the river or seabed. Workers can safely excavate and pour concrete inside the caisson to form a strong foundation below the waterline. There are several types like open, pneumatic, and box caissons, each chosen based on depth, soil, and construction needs. Cofferdams, on the other hand, are temporary enclosures built by driving sheet piles into the bed and pumping out water. This creates a dry work area where foundations can be built in place. Cofferdams are especially useful in shallow to moderate depths. Once foundations are ready, massive prefabricated bridge sections, often weighing hundreds of tons, are transported to the site by barges. Using powerful cranes, these segments are carefully lifted and placed with millimeter precision. High-tech positioning systems and coordinated teams ensure alignment and safety. This blend of underwater engineering and logistical mastery is what makes bridge construction across vast bodies of water not just possible, but incredibly impressive. One of the most essential elements is creating a stable foundation, often using pilings. Pilings are long, sturdy poles made of reinforced concrete, steel, sometimes even timber for shallower or less demanding conditions. Using massive hammers or vibration drivers, these pilings are driven deep into the earth, anchoring the future bridge with solid, stable support. Visual time-lapse of piling installation with underwater footage. With the foundations in place, the path is clear to begin building upward, constructing the towering piers, the bridge deck, and eventually linking both ends across the deep waters. 6. Foundation techniques: dredging, pilings, and temporary supports. Once piling begins, precision is everything. The number and spacing of these pilings depend on the weight and size of the bridge, the type of soil below the water, and the distance between support structures. In some cases, even dredging is required, a process that removes sediment and debris from the bottom of the waterway. Visual dredging vessels at work, scooping sediment. Dredging may be needed when the water is too shallow to accommodate the bridge design. The channel needs to be deepened for construction or future shipping. Visibility and precision underwater must be improved. Specialized equipment like dredgers, massive vessels equipped with suction pipes or bucket arms, are used to dig and remove material from the seabed. To provide stability during construction, engineers often install temporary support structures, steel towers, scaffolding, or floating platforms. These support the bridge as it's built out in segments, especially critical in cantilever construction, where segments are built from opposite banks and meet at the center. Case in point, during construction of the Kong-Zhuhai-Macau Bridge, engineers installed over 400 deep water pilings and dredged a vast shipping channel across the Pearl River Delta, a project spanning 55 kilometers 34 miles. 7. Bridge construction, segment by segment. With the foundation and supports in place, it's time to bring the bridge to life. There are two primary methods. 1. Prefabricated segments built off-site and transported by barge. 2. On-site construction using cranes and scaffolding. Visual bridge segments being lifted into place. Take the Øresund Bridge between Denmark and Sweden. Each section was prefabricated in a factory, floated out into the sea, and lifted by cranes into place before being welded together. This method saved time and ensured precision in every joint. 8. Testing and opening, ensuring safety and strength. Once the structure is complete, the bridge enters a critical testing phase. This may include simulated stress tests using weights and sensors, monitoring how the bridge responds to real traffic, ensuring that it handles vibrations, loads, and wind forces as expected. Only after passing all safety benchmarks is the bridge declared safe for public use. And finally, the grand opening, where the bridge is unveiled, celebrated, and opened to traffic, marking the completion of a complex and awe-inspiring engineering journey. Conclusion: the wonder of deep water bridges. So there you have it. From underwater site surveys to soaring spans above the waves, building a bridge over deep water is a feat of engineering brilliance, collaboration, and precision. We hope you enjoyed this deep dive into one of civil engineering's most challenging and rewarding projects. If you learned something new, hit that like button, leave us a comment below, and don't forget to subscribe to Civil Engineering Edge for more fascinating construction and engineering insights. Thanks for watching, and we'll see you in the next video. If you learned something new how deep water bridges are built, give this video a thumbs up, share it with fellow learners, and don't forget to subscribe to Civil Engineering Edge for more amazing civil engineering insights. See you in the next one.